Hammond mass in general, so like it's
Alright. So there's only two of us in the room as you can see, so I hope you guys really enjoy this recording. Well, Taha was beginning to write out a representation of SL2C.
a two-dimensional representation of it.
Yeah. Yeah, so we have a two-dimensional representation of SL2C.
Which I just said was the identity map.
Right, exactly.
Yeah.
Yeah.
But would it be the adjoint representation?
No, so we need to remember the definition of the adjoint representation.
Let me look up my notes. 1 second. Lie algebra. I don't seem to have it, unfortunately. Sorry.
I won't forgive you. You go to someone else if you're looking for forgiveness. You need more markers.
You want a red marker as well? I got that one in hand.
Let's okay, this one's nice. Yeah, so for any Lie algebra, the adjoint representation goes from G to GL of G.
Oh, so the adjoint representation would be GL of SL2C.
Yes, exactly. Right, and what does it do? Right, so where add x is given by the linear transformation where we put x in the first component.
Okay. Oh, and it's always like that?
Mhm.
Okay. So add is going from. Okay. So we can just apply that to just SL2 then, right? Yeah, I mean, is there any restriction on the second part though? Because it's not fully well defined yet. Can you just choose anything in there?
Sorry, what do you mean?
So like, you're trying to give like an explicit version, definition of the adjoint, function, so then, what would be the second component of the bracket then? Could it be anything?
There is no second component of the bracket. So what do I need to do to give you a representation, right? So for each x in X, I need to give you add x itself should be a linear transformation on G.
Yeah.
Right? So whatever add x is, it should be a map from the underlying Lie algebra G to G.
Oh, I see. So
And here's what the map is. What is that map going to do? So add x applied to an element y is going to be the bracket of x and y.
I see.
Mm-hmm.
Oh, okay, coolio. Okay. Yeah. Would there be like a canonical, sorry, I don't like that word. Would there be like a matrix representation of the adjoint of X?
Sure, yeah, so I mean, we could pick like we could figure out what all of these matrices are, right? Because we found a basis, we know that the dimension of SL2C is 3, right? So by picking a basis, what we can do then is I can write like add x for each of my, so it's confusing, I'm using x and y here, but then we also have like our standard
Basis
notation, yeah, x, y, and h. So what I can do is really for for each of X, Y, and H here, I could write add A, let's say, for any one of these. I could write this as a 3x3 matrix. That telling you exactly how it acts on the basis, right?
So A is just like any linear combination of these three of X, Y, and H.
Well, sure, but like, oh, you only need to know that X, Y, like, if we're trying to understand add from SL2C to GL SL2C, right? Then all I really need to do to get a grip on this representation is to tell you exactly where add sends
X, Y, and H.
X, Y, and Z, right?
Z.
Or sorry, H.
H.
And in order to do that, I could write these as matrices. Yeah, right, these are linear transformations.
Yeah.
So by picking a basis, and I may as well pick this basis, I can tell you exactly where I can represent each one of these as a 3x3.
Why would it be 3 by? Oh, because it's going from SL to S. Sorry.
Yeah.
Yeah. Okay.
Yeah.
Oh, I understand. And in fact, I have that because I not that exactly, but I know how to get that because I have the explicit derivation of where the SL2 bracket sends any two matrices. So we can just apply it.
Right. So if we choose to order our base, I'm actually, to follow a more typical convention, I'll order things as H, X, Y.
Okay.
Right, so we'll write our matrix in terms of H, X, Y, right? Where does add H send H?
Add H sends H to H bracket something, right?
Mm,
Oh, sorry, add H of H.
mhm,
0.
yeah. Right, so that would be 0, 0, so we'll be right. Here, yeah, where is it,
Wait, what?
what's, huh?
Why would a HX be 0?
This is, so remember, if you have a linear transformation between two vector spaces, right, the, like,
Oh, sorry, yep, sorry. Yeah, okay. Coolio. So it sends it to 0. H of X would be wait, H of X is 2x. So it's
Right.
2 would be, yeah. And then it would be 0, 0, -2.
uh-huh,
0, -2, 0.
yeah. Yeah. Add X, yeah.
0, 0, 0.
Mm,
I drink X
oh,
of
yeah.
X.
Yeah.
And then 1, 0, 0. No, negative. Yeah, no, 1, 0, 0. 1, 0, 0. And
And
then
then some things.
it would,
Well, I guess we may as well.
yeah, so this one would be 0, 0, 2. Negative 1, 0, 0. And then 0. Yeah, cool.
Yeah. So that is a really explicit way to write down this three-dimensional representation.
Okay,
Yeah.
and so you said that like the adjoint representation is the most useful representation. What is this telling us? Like that it's useful. Why is this being useful?
Well, my answer can be the same as for a lot of the questions last week. The classification theorem that we went through at the beginning,
Coolio.
right? So again, think back to that,
Coolio.
right? What we like, a lot of, basically the analysis came down to understanding how certain elements acted under the adjoint representation.
Julio.
And I mean, the other answer is You gotta do the reading on the representation theory of SL2C because that. That's sort of, well. Sort of the next step after we do that, the next step afterward is. Basically studying the adjoint representation of an arbitrary Lie algebra on it.
Coolio.
Yeah.
Nice. Homework done.
Yeah, homework done. What else did I want to say here? No. So in the, right, so for the two-dimensional representation, does it have a subrepresentation? Is it irreducible?
Irreducibility excluded the zero representation, right?
Yes.
I would think so it is. I don't know, just some intuition.
I mean, intuition's good, but at the end of the day, we need a formal proof.
We need a formal proof.
Yeah.
Okay, so for it to be irreducible, it meant that no proper subrepresentation existed.
Right.
And then. So suppose there was a subrepresentation
Mm-hmm.
that was also two-dimensional. Hi, Nestor.
Feel free to chime in at any point. Yeah, so. Are there any subrepresentations of the two-dimensional representation?
No,
Why not?
because if you want a subrepresentation, it would need to be a dimension lower, and the dimension lower is just like the trivial one. I'm assuming. Does that kind of make sense? That's my thinking kind of happening.
Close, it's not quite worded correctly.
Okay.
You're right. So specifically, a proper subrepresentation of the two-dimensional representation would have to be
a 1 degree representation.
right.
And the only 1 degree representation is 0.
Right. I guess technically we don't know. We don't know if there is there still could be, so we know that it can't be the direct sum of two one-dimensional representations.
Yeah, because
Right.
that's just the trivial.
Right, so it would have to be abelian.
Oh, okay, so right, abelian means the direct sum is a proper thing.
Nope. Nestor, what does abelian mean?
Oh, sorry, no, and like abelian implies that. Is that what you're saying?
Isn't abelian has to do that all the commutator brackets are 0?
Right.
Yeah,
Uh-huh.
so you're saying if it's abelian, then the direct sum of the two of the abelian representations would be is subrepresentation? Is that what your earlier statement was? I'm just like
No.
Okay, never mind.
Other way around, so if it were the direct sum of one-dimensional representations. Right, well, we know, or maybe it's something you should prove, the direct sum of two abelian Lie algebras is again abelian.
Yeah.
But this is definitely not abelian.
Yeah, no. And the one-dimensional one definitely is.
Right. Yeah, so it cannot be isomorphic to the direct sum. Now, actually, by some later theorems, it's enough for us to know that, but technically, a priori, this doesn't rule out the case that it still has it could still have an one-dimensional subrepresentation. Right, our argument just tells us it's not isomorphic to the direct sum of one-dimensional.
Oh, I see.
But maybe there is a one-dimensional subrepresentation that sits inside of it in a more complicated manner.
But a one-dimensional representation in this situation would just be a 1x1 matrix.
No, so.
You're your own cameraman today.
So. Remember, the representation we're talking about is just. You know, the identity map from, well, SL2C to, you know, GL2C, basically, the inclusion map.
Yeah.
Right? So what is a subrepresentation?
A subspace of GL2C.
No.
Sorry.
So remember, a representation is a vector space together with a homomorphism, right? In this case, well, maybe it's, sorry, maybe I should write it this way, right? In this case, the vector space, the underlying vector space is C2.
Yeah. C2 row.
Right. So what's a sub-representation? By V sigma. Right, so sigma is a map from G to GLV. What does it mean to be a sub-representation?
I'm just shooting in the dark here. Would it be just a GLV is isomorphic to a subspace in GLC2?
Okay, forget this,
Okay.
for a second. Definition of a sub-representation. So a representation is a pair, right? It's a vector space and some map, subject to some conditions. So a sub-representation should have something to do with this pair.
Yeah.
Right?
So V has to probably connect to C2 and then sigma probably.
No, forget everything up above here for now. Everything above this line, forget it for a second. Okay,
Forgotten.
in general, we need to know what the definition of a sub-representation is. If we're gonna have any hope of finding what one is, right? So a sub-representation
Would have to be.
a representation is a pair.
Mhm.
Right? It's a
Yes.
vector space and a homomorphism from the Lie algebra into GL of that.
Yeah.
Okay,
Is suburb.
so if you're going to tell me of something what a representation is, you better give me a pair of things.
Mhm.
Where the first thing was a vector space and the second thing was a home.
Yeah.
Sub-representation should be a representation.
Yes, first and foremost.
Yeah. So, in other words, I'm asking you what you think a sub-representation would be, and your answer had better be some pair of things subject to some conditions.
A vector space W and a map,
But now also, it's not just a representation, right? It's a sub-representation of V sigma, so somehow it should have something to do with V sigma.
would it be W sigma, where W is a subspace of V?
Okay, it is a. So
Is it
a subspace. W of V. Certainly. Is, so maybe let's say, yeah, a subspace, and what else should be true?
Oh, sigma restricted to W should still be a linear transformation, or that respects the bracket.
Yeah, so where, let's say it this way, for all x in G, sigma x takes W into W. Or in other words, where for all x in G, for all W in W, sigma x W is in W. Right, so W is closed under the representation. Okay. So now I want to see if there's a sub-representation of C2.
Well, then it needs to be a subspace of C2.
Right. So what would a proper subspace of C2 look?
C. Or
Well, yeah, yeah.
constant, right? Because C2 is a like it's a two-dimensional vectors, like it's vectors with two components, so if you want a proper subspace, then you would just need like only one of the components. Yes, no, no, have I forgotten all of linear algebra? Probably.
Yeah.
Okay.
So what would the dimension of a proper subspace
Below two,
be? Yes.
which is, and I'm assuming we're excluding zero. So it's
What's the zero, how many zero-dimensional subspaces are there?
one,
Right,
so just.
and it's the zero space, which is trivial, right, so that wouldn't be a proper. Yeah, normally, for proper, we say non-trivial to mean not zero and not the entire.
Yeah.
Yes.
So it would just be a one-dimensional subspace.
Yeah. Okay, so a one-dimensional subspace of a vector space. Well, what do we know about one-dimensional spaces in general? Well, like what does it mean to have dimension n, for example?
Only one base, it has n bases elements.
Right, so there's a basis with n elements in it. So if it's one-dimensional, there's a basis with one element in it. Right?
Mhm.
In other words, a subspace, right? So right, it's just gonna be the span of some xy where x and y aren't both 0.
Yeah,
Okay, but what else would have to be true for this, in order to have a sub-representation? And maybe let me change some of the notation here. I'm gonna rewrite these x's with a's because we're using x in a very particular fashion.
well, it would need to be closed,
Right,
yeah.
right.
So for all A in your Lie algebra, and for all W in that spanning set,
Mhm.
sigma A of that W better be that.
Right,
Oh, it must be a constant multiple of it. Sigma of any element in your freaking Lie algebra should go to a constant.
constant multiple of the vectors.
Wouldn't it go to a constant multiplication map and then that map applied to any W in vector W in the space W would keep it in there. So here's what I'm
You might have the right idea, but your words are very.
okay, here's what I'm trying to say. So
Oh, here, use the black marker, it'll probably come up better on the board.
okay, so here's what I'm trying to say, correct me if I'm completely out of the woods, so we need, let's let. Sigma be.
Maybe write a bit bigger, there's
Yes,
there's viewers watching at home. Maybe I'll
Let's-
zoom in.
sigma be a, let sigma be from. Or space G. To, GL. Of what vector space are we working on? W,
C2.
C2. Wait, no, I'm talking about the sub-representation now, so wouldn't it be W then?
So let's look at our definition.
Sub-representation of VW, V sigma. So in our case, it's C rho is a subspace W of V. Okay, where for all A in G,
Yeah,
for all A in C2,
and you're right, I suppose specifically, I should have specified that it's gonna be W and sigma. Well, just W sigma. Be the pair, right?
yeah. And you said that we're looking at rho being the identity map, yes?
Well, it's the inclusion, it's the inclusion.
Inclusion. Yeah.
Picking a particular basis.
So, what I'm saying is that rho of any W that's in here, okay,
That doesn't make sense.
that doesn't make sense, you're right. Rho of anything in C2, in SL2,
Yeah.
not A,
Yeah,
applied to any W
yeah,
should equal a constant, I don't know, Z W,
yes,
where Z is in C,
yes,
and then A is in SL2, C.
yeah. This is true.
Yeah, and so we know exactly what happens with this, we know what this does exactly. But wait. You're looking for eigenfunctions. Sure. You're literally, because this is. The row of A is a better be a freaking eigen yeah, an eigenfunction of W. Anything in W. I don't know if I'm wording that right. Like.
Okay, let's. Yeah, that's a good observation, not a bad observation, but. Let's not lose focus of what's in front of us,
Okay.
right?
So what would we do?
What do we want to know? We want to know if we can find a sub-representation of C2.
We want to find W.
Yeah, we want to know such a thing exists. We know that if such a thing exists, it's just the span of a single non-zero vector. And if it really is a sub-representation, then for our representation row, this statement that you've written had better be true.
Yeah,
Okay. How could we verify that that is true?
Test it out.
Test it out. Yeah,
Oh, okay. So we would have to pick an A. And then let W be general, and then see if it actually ends up being a constant multiplied by that.
yeah,
Yeah. And does it matter what A we choose?
no.
So why not just like I don't know, H?
Sure, yeah.
So row of H. We know that that is the map. No,
No,
that one, this one. It's 1 0, 1 0 0 -1.
yeah,
And so that multiplied by W, put it here, XY. That gives you X -Y, which is
Mhm.
not Z times XY,
why not?
because
Can you give me a formal proof instead of jumping ahead to a claim?
suppose in hopes of reaching a contradiction.
Sure.
Suppose in hopes of reaching a contradiction that this actually equals a Z times XY.
Yeah,
So then that would mean that X is equal to ZX
sure,
and -Y is equal to ZY.
uh-huh,
We said that they're not both 0.
okay.
So here I can divide by X on both sides. That would imply that Z is equal to 0. I can divide.
Whoa, we said they're not both 0.
Oh, okay, 2 cases.
Yeah.
Case 1. X not equal to 0. That would imply that Z is equal to 0. And
Why?
because I divide both sides by X.
X divided by X is,
Oh, sorry, X, I'm stupid. 1.
sure,
Okay, and then Y could be 0, but so then I would also, from substituting in 1, I would get -Y is equal to Y, which then implies that Y is equal to 0,
okay,
which is a contradiction in this case,
why is that a contradiction?
because then both are 0. Wait,
No,
sorry, someone's calling me, 1 second. Wait, no, that's fine.
yeah, nothing wrong with that,
Okay. So that's, oh, okay, so that's potential W,
maybe,
okay. So potential W is X0. Where X is non-zero,
yeah,
okay, but then case 2. It's where Y is not equal to 0. Then Z is equal to -1. And so X would be equal to -X, which then implies X is equal to 0. Okay, so we have 2 potential things where W could be span of I guess it would just be 1 0,
yeah,
or span of 0 1. Yes,
yeah,
cool. Done? Are these wait, no, but then we would actually have to prove that they're actual sub-representations.
right,
This is isomorphic to C, no?
as a vector space,
Yeah,
okay,
so either way, W is isomorphic to C. WC
as a vector
as a
space,
vector space.
sure, Are we trying to find a subvector space?
No,
No, I mean, partly, but what are we trying to find?
we're trying to find a subspace of C2. So that satisfies.
Well, that's part of, yeah, okay, that's other sentence you just said there is very important, right? It's not a subspace, it's a subspace that satisfies those conditions.
Wait, try it for another thing in thing, okay.
Yeah,
Can I erase that top part?
sure, go ahead.
I don't wanna erase the definition. I'm sorry that this ended up just being me trying stuff out instead of it being like an actual lecture. Sorry, Nestor, and I'm sorry that I'm slow. Okay, so if I do row of, I don't know, take X. That would be just 0, 1, 0, 0. Apply it to W.
Well, we've got two candidate vectors,
Yeah,
you know.
yeah, so this is that, but then case one. W equals to span of 1, 0.
Mm-hmm.
Then row of X applied to W would be equal to 0, 1, 0, 0 of X 0, which is
Well, yeah. Yeah,
which is fine, because
That's
that's
fine.
there.
that's fine.
That's fine. Okay, case 2. It's that W is equal to span of 0, 1. Row of X of W is equal to 0, 1, 0, 0 of 0, 1, 0 Y. Which is just. What? Oh, Y 0,
Mm-hmm.
which is not. Which is not in W unless Y is equal to 0.
Right. But
Well, we can't have Y equal to 0 because this needs to hold for everything.
yeah, so the part of the thing is, there was no, you didn't need to write the X or the Y there, right? All you really needed to do, like in this case, is just check that the one vector, when you apply it, doesn't land back in W, right?
Yeah,
Cause we're proving it's a for all, there's two for all statements, right? For all A and G, for all W and X, so if you're disproving this, you just need to say there exists, right? So you don't need to write like a very general vector like 0 sub Y, right?
yeah,
You just needed 0, 1.
yeah,
And just to conclude that 0, 1, cause then, yeah, the Y definitely isn't 0 if you're looking at 0.
yeah. So this one, the case 2W, this one fails.
Right.
And I see it in my brain.
Yes.
If I just did PY
Right,
for the first case, then it would just end up with a contradiction as well. So there is no sub-representation.
yes, exactly.
Cool.
We did it.
Okay, so no sub-representations of the two-dimensional representation of SL2.
Uh-huh. So what
Using the identity map.
yeah, so what can we say about that representation?
It's irreducible.
Yeah, it's irreducible.
Would any representation of SL2 be irreducible?
I'll leave that to you.
Okay, well,
Can you come up with a representation that has a sub-representation?
I will think on it. No.
Well, let me ask you this. Would, well, I guess if it's just for SL2. Yeah, okay, I'll leave it to you to think about. Okay. Well, what should we do in the remaining 20 minutes? Because.
What would be next on our list?
Well, the thing is, the thing to do, the reason why I wanted the homework for this week was to go through these examples. Is because I was hoping we would get through the reading as well, which is, reading about the general representation theory of SL2.
Okay, so that's homework, question mark?
Yes. Yeah, because the idea is you should apply these representations and the reading is sort of abstract about how the representation theory of a Lie algebra works, right? Or at least of SL2, how we carry out the analysis of representations of SL2. So the idea then is that you have these examples to apply the abstract theory to.
Oh, I see, so this is just like like. So the fact that there is no sub-representation of C2 row for SL2, we can abstract that a bit more using the reading.
Well, not that specific fact, but I mean, the reading will tell you something about irreducible representations in particular, but also just how to carry out an analysis of representation.
Okay.
Yeah, so it's just, by having this, you can, the idea is you can just have these concrete examples to plug into this general analysis of representations of SL2. And then if you happen to see a theorem that says something about irreducible representations, well, now that we've gone through this part of the exercise, you have that extra factoid and you can plug it in to, explicitly understand whatever theorem they have about irreducible representations.
Coolio. Kind of a trivial question, but like the
All questions are trivial.
oh my gosh,
No,
is this trivial? Oh my gosh. The zero representation is always irreducible, yes?
What do you mean about the zero representation?
Like that that sends the take any vector space B
Yeah,
and the map sigma, where sigma is taking you to the zero element.
right, okay.
So that is always irreducible. Yes?
Well, let's try and prove it.
Okay.
Yeah, erase this board and prove it. Let's use the definition, so.
So that she used black visible.
Yeah.
So so do we want to prove it for any Lie algebra G then?
Yeah, let's get as general as we can. Take a Lie algebra and a vector space.
Let G be a Lie algebra.
Yeah.
The algebra. Let B be a vec space,
Sure.
and then let sigma from actually, sorry, I'm gonna change my notation a bit. 0 be the map from G to GL V
Yeah.
such that A gets mapped to the 0 dimorphism.
Sure, you can just write 0.
0? Okay. Cool. And then statement. V
0 is irreducible. Reducible. Yeah, I'm getting proof by contradiction vibes, yes? Cool.
You tell me, you tell me.
Well, I mean, whenever you wanna say that like something can't happen, show that if it does happen, something wrong happened, like that's, yeah.
Okay,
To prove. Suppose in hopes of reaching a contradiction that W 0 is is a subrepresentation. Subret. So that means by definition that for all. That means that W is a subvector space of V and for all A in G. For all W in W 0 of A of W is in W.
yep. I agree.
Zero of. Wait, no, that's always true though.
That's always true.
Oh, so it's, wait, so what? So the 0, so this is reducible as heck.
Unless,
This is the 0 vector space?
well, there's the 0 vector space or. I mean, what does it mean to be a non-trivial subspace?
There's a lot of definitions on it. I mean, like you can say you're a vector space, you're a subset that is also a vector space. You have those.
So a subspace of a vector space
Okay,
is non-trivial.
non-trivial closed.
If it's non-trivial, there's two things that we don't want it to be.
0 and the entire vector space.
Right.
Yeah,
Mm-hmm.
so. What would be the one vector space such, so we already know that the 0 one is irreducible. If the vector space is 0, then it would be irreducible because there would be no such subvector space. But what other vector space doesn't have any middle vector spaces?
Yeah.
That's your question? There's a word for it. Wait, don't we just call them irreducible? Isn't that?
No, there's no such.
There's no such thing, okay. A one-dimensional vector space?
A one-dimensional vector space.
Okay,
Yeah. So that would be irreducible.
okay, so this is irreducible if and only if, so I guess the proper statement is this is irreducible if and only if dim V over its field K is equal to 0 or 1.
Yeah. And in fact, we normally drop the case when it's 0. Because it's almost too trivial. It does end up popping up in some places, but normally we always assume our representations are not on the 0 vector space, but there's some weird occasions, including I've seen it in my research where like you actually need the representation on the 0 vector space for something. You know, it's kind of like in the way that most of the time we do not think about the empty set.
Yeah.
We exclude the empty set, but then there's some really weird edge cases of stuff where we need to consider the empty set for some reason.
Sick.
Yeah, great. Right.
Anything in particular that you wanted to, I mean, if you want, we can like us to go over like the general representation theory that you mentioned earlier.
Yeah, I suppose so. So let's see, we were gonna switch to Hall, but I think actually Fulton Harris. Unlike Hall, I think Hall decides to focus on SU3. Whereas, wait a second, is that isomorphic though too? Whereas Fulton Harris writes it in terms of SL2.
He kind
Yeah,
of
but-
SL3 and SLN.
Yeah, so maybe we could look at Fulton Harris first. But so here's something worth pointing out. You have to remember your linear algebra. So. The point is, well, so we're looking at, we're supposing that I have some representation. Of SL2C, right? And, you know, we're assuming, say, V is finite dimension. Okay. How should I word this? Yeah, I don't, This is troublesome because it actually relies on some more fundamental results that we decided to skip. Now I'm regret, I thought we could get away with it, but now I'm starting to regret it. Yeah. Okay. Gosh. Maybe we do need to go back and read some more basic theorems. Part of the point is this. So in linear algebra, we study two kinds of matrices. There are matrices, well, broadly speaking, there's matrices that are diagonalizable, and there are matrices that are not diagonalizable, right? And it turns out there's something called you know, Jordan decomposition, where basically you know, we can write all of our matrices in such a way, right? So any matrix we can split up into a diagonal part and what's called a nilpotent part. So D here would be a diagonal matrix. And N is some which makes that matrix equal. And oh gosh, yeah, maybe we'll have to go back and actually, okay, I'm gonna have to look because maybe Paul gives us a way to circumvent this more basic theory, maybe not, I don't know. So the point is, well, at least maybe this is believable, but it's a strange, it's maybe a priori strange theorem. So let G be a matrix Lie algebra. Okay, then if that's true, if G is a matrix Lie algebra, which is to say isomorphic to a subalgebra of GLNC for some n, then if x in G or let's not even take isomorphic, that's the more general definition, but let's just say it is a subalgebra. Then if X in G, now the X is a matrix, is diagonalizable, then so is row X for any representation. V row. So what does that mean? Oh, what does right? Suppose I have a vector space, and suppose I have some linear transformation. I have some matrix D, which is diagonal with respect to some basis, V1 up to Vn. And let me write D as this diagonal matrix D1 up to Dn. Then what happens when I apply D to Vi?
Sorry, I zoned out for a second. D diagonal with K.
With respect to a basis V1 up to Vn.
That's diagonal, so that applied to V. That would be D1 Vi. Sorry, Di Vi.
Yeah, exactly. Right. So in other words, I mean, this is basically an eigen basis for this linear transformation. Right? So that means, going back and looking at this theorem, what this means is that if I have some matrix, right, and I write out this representation, I know that my diagonal matrix, like I know that I can find some basis of my representation so that that matrix acts diagonally, right? Actually, I could probably just stay on this one because you're the only one in the room writing, so there's no point switching points. So what does that mean? That means, so we have our, so let's go back to SL2C. And we have our representation V row. And I know we have this basis, right? We have this nice basis with these nice relations. And H is diagonal, right? So therefore, we can find a basis, right? Hence, there exists a decomposition V into the direct sum over some set of, say, so I'm going to call it alpha in lambda, the alpha, where V alpha is the alpha eigenspace of row H. So this is very important. This direct sum I'm writing here, I do not mean a Lie algebra direct sum.
You mean it?
Or I do not mean a direct sum of representations. I just mean this is a direct sum of vector space. Right? So I'm just using a fact from linear algebra that I can decompose my vector space into direct sum of eigenspaces for my diagonal matrix.
Interesting.
Right? So there's two things that we can do in hopes of a general theory, a general way to try and understand how our representation is going to behave. So one, we can just look at, if we have some explicit representation, we can just look at whatever row H is. I mean, this is just going to be one matrix, really, and figure out what its eigenvalues are. And do the normal stuff you do in like algebra 2, right? Find the dimension of the eigenspaces, all of that stuff. And then we can get some structure. We can sort of understand how this might break up. And then the other thing to understand is how our other two basis elements act on here.
Oh, yeah.
So what I mean by that is suppose V is in the alpha eigenspace of H. And consider, so sometimes we just write XV to mean, of course, I mean row of XV, right? But we might just write XV or X dot V as a shorthand. Right? So let's try and figure out what happens to this thing, right? It's either maybe it just lands back in the same, like maybe it turns out this is actually a direct sum of representations, right? Maybe it does split up according to the eigenvalues. Or it might end up living in a different eigenspace, or it could even live in a direct sum of eigenspaces, right? It might spread out the eigenvalues. Yeah. But how could we possibly tell? Well, we act by H. Right? Because if we act by H and it spits out, we can decompose it as some sum of other eigenvectors, that will tell us exactly what we want to know. Right? So let's see what happens. So if I have H acting on X acting on V, well, how could I rewrite this? How could I play around with this and maybe find out some improvement?
The acting is just taking it in as an input, right?
I don't know what you mean by that.
So this is really representing row H of row X of V.
I mean, yeah. Okay, I'll put in the row if yeah. So this is what we're doing.
Oh, times?
Well, I mean,
Okay.
like this. Acting on this.
Yeah. Yep.
Yeah.
You're not necessarily included.
But we know something about H and X.
Your basis elements.
Yeah. I mean, we know something more particular about their relationship to each other in SLTC. How do we try and turn this into an equation that involves what we know about H and X? What is the thing we know about H and X, the relationship in SLTC?
Linearly independent?
Sure, that's true.
Like what relation would be useful in this situation?
That's a good question.
That I guess that acting on C itself.
Don't know what you mean by that. I don't know how they act on C.
sorry, C squared,
Yeah.
I don't necessarily got any of this. I don't know. Are you talking about their bracket with each other?
That would be a relation.
The bracket of those two would spit out as some constant times n. Yeah, that's
Well, not some constant.
in this case two.
Yeah. Maybe that's a useful thing to know. How would we turn that into information?
That's part of the commutator.
It looks like part of it, right?
Yeah. So,
But also this is happening, this is something that's happening in the target, in the vector space. What could we do to write this? Like, we need to talk about H and X happening in SL2C.
what do you mean by happening in our, like this multiplication is happening in our vector space, yeah.
Yeah.
Well,
Okay,
and then
like-
row H, row X would be just some matrices with coefficients in B.
Yeah, those are some matrices. Let me do one step of this. Let me just re-bracket things here.
Okay. Row of H composed with row of X. I don't know, we've never like composed the map for the representation.
No, what's a representation?
It's a vector space and a linear transformation.
Right, well, no, that's only part of it.
GOV, such that it respects the brackets.
Aha, right, so what does that mean? So first off, yeah, so,
For all A and
right,
B.
so this is first off, it's linear.
Yep.
And, what else is true for all X, for all A and B
in G,
in G, row of
A, B
the bracket.
is the bracket of the rows.
And in particular, what is the bracket in GL?
The commutator.
Right, the commutator of
Row A, row B minus row B,
right, I mean, this is the composition of these linear transformations, right?
I guess, yeah.
I mean, the matrix of a composition of linear transformations is the product of the corresponding matrices.
Yeah.
Okay. So, I mean, if it makes you happier, I'll write this as a product of matrices.
Okay,
Yeah.
and so, yeah, this is exactly what I said earlier, that this is just the first half of the commutator.
How could we get the other half of the commutator?
Add and subtract,
Sure,
do the zero trick.
sure, exactly. Look, it's the greatest trick in the from the most advanced and most basic math. That's the, only trick we know a damn thing about. So it's this minus this plus this,
Yes.
and all of that times v. Okay, now what?
That's row H bracket X,
Yes, this is row of H bracket X.
which is just 2x.
Uh-huh.
We'll get to that.
Well,
Jumping the gun.
yeah, and then over here we have row X, row H.
B.
Yeah,
So that turns into row, or I guess since row is linear, 2 row X
yeah. So this is 2 row X
plus row X row H
plus row X, row H. Uh-huh,
V.
yeah.
Factor out a row X, question mark?
Yeah, we could factor out a row X, sure.
2 plus row H.
Yeah,
Take the V in.
sure. Yeah, so this is row X. 2V plus row HV.
Row HV is in V alpha.
Right, so what does that mean? What is row HV gonna be?
An eigenvector?
Well, yeah, more specifically,
Oh, row H times V is gonna be a constant times V.
yeah, what constant?
Alpha.
Yeah. Right, so what is this? This is 2 plus alpha V. Right, or to rewrite it, this will be 2 plus alpha times row XV. Right?
Yeah.
But remember, the thing that we started with was row XV.
Yeah.
And we acted by H. Oh, so we get out an eigenvector. Right? Row XV is an eigenvector of H of eigenvalue 2 plus alpha.
Okay. Coolio.
Right? So what that means is we have our representation, right? V alpha. If we act by X, that's going to take us over to V alpha plus 2. That's what our computation just showed.
Wasn't that specific to X though?
What do you mean? Like, yes, that's exactly what I mean,
Okay. Coolio.
right? We have something in V alpha, we act by X, we get something in V alpha plus 2. But our choice of alpha was arbitrary, right? So do it again, we're gonna get what?
Alpha plus.
Yeah. Right, and it's gonna keep going until eventually we hit 0, right? So there's gonna be some, alpha plus n, which will be our sort of highest non-zero eigenspace. What do you think y is gonna do?
Alpha minus 2.
Right? And that's gonna go this way, so. So for SL2C, all we need to do to understand the representation, we have this one element, I mean, it's this three-dimensional vector space, all these infinitely many things. We have this one element H. If we can find its eigenvalues, then that completely determines the representation. Right?
Oh.
Because we know all we need to do is now take any vector, decompose it in the eigenbasis, and we know exactly what x and y are going to do. They're either just going to move us up or down by multiples of 2. So that's a good place to leave it, I think, and probably some good, this should allow you to understand what the hell Fulton and Harris are talking about. And so even without digging into Fulton and Harris, well, you should read that chapter on SL2C. But remember, we have concrete examples of representations. We have at least two, right? We have what we might call the standard representation, which is just, yeah, SL2C, remembering that those are, acting on C2. And we have the adjoint representation. And now we can look at both of these things and sort of ask ourselves, so yeah, what are the items, right? And now there's all sorts of questions we can ask, like, okay, well, what is the basic alpha that shows up? Like, there seems to be like, there's gonna be two numbers, right? There's some n, alpha plus n. And there should be some other one that's gonna be like alpha minus m, right? That will be sort of the smallest vector space before you hit the zero space, right? So we sort of have this trail of vector spaces, right? So for each representation, you might ask, well, what is the alpha, right? As we change our representations, what are the alphas that show up, or, so it seems like maybe all our representations are labeled by m, n, and alpha, right? There's sort of like one number that you pick for the fundamental eigenvalue. Well, yeah, I would argue that you could you can determine some things about this already, and n and alpha. So we might hope, right? Our hope is basically, does this completely characterize our representation? What are the choices of m, n, and alpha that are possible? Can can we have two representations that are not isomorphic that have the same m, n, and alpha? Or the other thing we're interested in is finding irreducible representations, right? So we might ask, is there some way that we can know if our representation, because really knowing our representation now just comes down to these three numbers, m, n, and alpha. So is there some way that we can look at these numbers and know if our representation is irreducible or not? Yeah, maybe that seems possible. Anyways, I guess that's it for today. So, yeah.
Yes, thank you.